common misconception among most lay people and even some experts is that my job is to prove a theory, say prove inflation right, or prove the ekpyrotic model or bouncing cosmological model or ADS. And it's nothing of the sort. My job is to disprove theories. The more, the better. We don't have a notion of proof that would suffice for a philosopher like you or a mathematician. It cannot be accomplished in the physical sciences. And yet, what we can do is disprove a panoply of competitive theories, which, if true, would perhaps revoke or promote a given model of cosmogenesis. And that's what makes my job exciting. I get to be a professional exterminator, killing off rival theories and working towards the betterment of understanding of how things might have taken place.
Hello, this is Robinson Earhart, here with the introduction to Robinson's podcast number 195. And this episode is with Brian Keating, who is the Chancellor's Distinguished Professor of Physics at the Center for Astrophysics and Space Sciences at UC San Diego. Brian is also the host of the terrific Into the Impossible podcast, where with a roster of 19 Nobel Prize winners, among many other terrific guests, he's absolutely demolishing me in that department. And then he's also an expert on the cosmic microwave background and the author of a number of books, the most recent of which is Into the Impossible, which is a distillation of many of his conversations with Nobel laureates and some of the aforesaid other brilliant thinkers that he's spoken with. Now, before our conversation, I read another of his books, which is Losing the Nobel Prize, which was great if you'd like an overview of the history of expansion and the theory of inflation, as well as a better understanding of the Nobel Prize. But in this episode, we get into expansion and inflation as well as the relationship between theory and experiment in cosmology, gravitational waves, Brian's brainchild, the BICEP experiment, and a lot more. So in the description, you can find links to Brian's YouTube channel, the Into the Impossible podcast, and then Brian's mailing list, which you should definitely sign up for as well. So one correction I have to make is that I mistakenly referred to gravitational waves as gravity waves a number of times. These are not the same thing, though Brian explains the difference. And then one last thing is that we actually recorded this podcast quite a while ago, and I've wanted to have Brian on the show for a very long time, and I'm already very much looking forward to the next round. So there is a Patreon for an ad-free RSS feed, reviews, comments, likes, subscribes. These are always greatly appreciated. And now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Brian. I've talked to a number of astronomers and astrophysicists on this show, and at this point, and please correct me if you feel otherwise, but I have the sense that there are at least 4 groups among them. There's theoreticians, there's observers, there's instrument builders, there's experimentalists, and they overlap. But just to start off, what was it that gripped you so much about the building and the seeing? Because from the way that you write and talk about Galileo in your book, Losing the Nobel Prize, I can see that it's really a romantic, serious love affair.
Yeah, I mean, for me, the notion of contributing to the corpus of scientific knowledge, really initiated by Galileo is really too much to wish for. And yet, here we are, or I've come very close to, making measurements along with my colleagues and friends and team members using a Galilean refracting telescope exactly of the character that Galileo himself used in the skies of northern Italy in 1609. And so it fills me with overwhelming awe and dread to follow, clumsily in the footsteps of your heroes. And yet the contribution I think I'm most capable of making is in regard to the acquisition of data. And I think a common misconception among most lay people and even some experts is that my job is to prove a theory, say prove inflation right, or prove the ekpyrotic model or bouncing cosmological model or ADS. And it's nothing of the sort. My job is to disprove theories. The more, the better. We don't have a notion of proof that would suffice for a philosopher like you or a mathematician. It cannot be accomplished in the physical sciences. And yet, what we can do is disprove a panoply of competitive theories, which, if true, would perhaps revoke or promote a given model of cosmogenesis. And that's what makes my job exciting. I get to be a professional exterminator, killing off rival
Mhm.
theories and working towards the betterment of understanding how things might have taken place. So that's the attraction to me. I'm kind of an optimistic pessimist, and it's really fun to show that people are wrong and do so respectfully and do so openly. In other words, I should test inflation. I should test competitor to inflation. I should not come in with any preconceived biases. It's very hard, when you know that having a null result, when you essentially do not say anything conclusive about the parameters of a given theory, say inflation, which predicts a very specific pattern of the polarization of the cosmic microwave background. If you were to detect that, obviously that would be huge evidence in support of inflation, but not proof, but still huge support. And then all these ancillary benefits follow from it: fame, attention, Nobel prizes, the glory of seeing the first moments after the Big Bang. So it's intoxicating to be able to do that, but at the same time, you have to be careful not to let your kind of inherent biases as a human being. Now, that's the biggest misconception. People think scientists are just chat GPT, bots that just dispassionately evaluate evidence, where nothing could be farther from the truth. We have tremendous biases, and the earlier and the more seriously we recognize those, the better science is and the better we are. And I think that ultimately accrues to the benefit of society.
Hmm. Yeah, fame, attention, and Nobel prizes are all things that we all want. So, and just when human psychology enters the picture, then that leads to confirmation bias. So you're performing a very valuable service. I hadn't realized before reading your book that the goal of the observer, the experimentalist, the instrument builder was to disprove theories. But among other things, that was the most important thing I think I took from the book. The other was the word schlemazel, which I had never never heard before, and I pronounced it schlemazel because I liked that better. But then somebody told me that I was asking about the word, that a schlemiel. Maybe you can correct me. A schlemiel is someone who spills water on somebody at a dinner or wine or something, and the schlemazel is the person who's always getting spilled on.
Yeah. So you probably heard the word mazel tov, right?
Yeah, yeah.
Usually people think that means congratulations. It actually means mazel means constellation in Hebrew, and
Hmm.
tov means good. So mazel tov means good constellation. What the hell is that? Not only do I like that because it connects to astronomy, but of course, the shlemazel is actually a Hebrew word, or conjunction of Hebrew words, which is Yiddishized, and then shlemiel is completely Yiddish. And I know this is boring 99% of your audience, but anyway, shelo mazel means means that person. Lo means no in Hebrew, and then mazel means constellation, but really it means luck. Like a disaster is a bad star, right? But that means bad. Something bad happened. It doesn't mean there's a negative star over there, because people thought the stars influenced their daily lives. And similarly, if you get soup always spilled on you, then yes, you have no luck. You have no mazel tov. You have no good luck. You're basically bad luck. I think shlemiel, I don't know. It must mean, has no grace or something like that. Yeah, something like that. I don't know exactly the origin of it, but it's used for, spilling of soup. And it was popularized in Laverne and Shirley. It was part of their theme song.
Hmm. Well, your religious history is quite fascinating. I don't know if we'll get to it today, but it's all in losing the Nobel Prize. And actually, my audience loves etymology, so please feel free to bring this in at any point. But so you've already mentioned a couple of things that I'd really like to talk about. The Nobel Prize is one, but cosmogenesis is another. And toward introducing your experimental work with BICEP and BICEP 2, I mean, there was a huge and rich history of astronomy before expansion and inflation were introduced or discovered, depending on how you look at it, during which time our view of the universe continually expanded. I mean, first to include new planets and stars with Galileo's use of the telescope, as you write about in your book, and then ending around the time that Hubble discovered that Andromeda was a galaxy. But how was expansion itself discovered and the Big Bang Theory formulated? I think that's where we need to start to get toward BICEP
Yeah.
and BICEP 2.
So the essence of the Big Bang was really codified over a period of about 12 or 13 years, which is a really short amount of time to have a revolution that upended the, overused term paradigm shift that had prevailed for literally all of humanity, essentially. It believed that the universe was eternal, static, unchanging.
Mm.
So to upend that in a mere 13 years is just astounding. And it was really a combination of the two aspects that you mentioned originally, two of the three aspects of astronomy, which are theoretical and observational, and the third being experimental. That didn't play a role until the later discovery of the cosmic microwave background, which is my expertise, in 1965. So from 1915, when Einstein started to conjugate the laws of general relativity, which would provide a framework for people like Alexander Friedman, and colleagues, as well as this George Lemaitre, who's a Belgian Catholic priest,
Hmm.
to apply mathematically a justification for why the universe couldn't be static. And Einstein actually knew that. Einstein knew the universe was dynamically unstable, and that it could be either it could be expanding or collapsing, but it could only be static if and only if there was an exact repulsive force of gravity to counteract the known amount of matter that he knew about. He didn't know about other galaxies, but he knew our galaxy was made of matter, and he knew we saw light from stars, so there was at least matter and radiation. And matter and radiation are both attractive. Even radiation is an attractive component of the universe's energy. So he, and as a consequence of general relativity, which he had devised over 5 to 7 years, he realized that the universe model in his conception, 1917 or so, was unstable, and he had to stabilize it. He added in a term which is essentially a vacuum energy term, a term that meant the universe was suffused with an energy, unseen energy, effectively what we call dark energy today, that didn't interact with matter or radiation, and provided a negative repulsive gravitational force to suspend the stars in their place. And again, he didn't know about external galaxies that we'll talk about in just a bit. And you mentioned it with respect to Hubble, but that was only discovered in 1923 that Andromeda was an external galaxy, not a nebula within the Milky Way. So Einstein's conception was that the universe was static based on observation. It sure looks static. In fact, I pointed this out to Joe Rogan, and I pointed out many other instances. But the fact that we only had five things that people talked about as movers, and that term and the etymology is planet, which I also realized recently. One of my kids pointed out, well, plane is just the word planet without a T. I was like, what is a plane? Like, why do they call it a plane? That flies you through the air. But it's really based on planet, which means wander or mover,
Huh.
and in Greek. So the etymology of that word is Greek. So the fact that the ancients named these five things, they could see Mercury, Venus, Mars, Jupiter, and Saturn. They named those things planets, meant that those weren't things that weren't moving. So basically, everything they knew was static except for these five objects. So that was very puzzling. And so what ended up happening was Einstein said, let me take the data, I'll fit it to my model. oh, I need this bizarre term called dark energy. And reportedly, George Gamow later said that he called that his biggest blunder. We actually can't find any written literature where Einstein says that himself. Putting in of the cosmological vacuum term was my biggest blunder, but it's generally accepted that he did that. I point out many times that because in 1997, two groups of colleagues and friends of mine that have been on the podcast, my Into the Impossible podcast, many times, they discovered that there is a form of dark energy that does pervade the universe, and it may be a cosmological constant, just like Einstein said. So the biggest blunder that Einstein made was rescinding his prediction of the cosmological constant. And he did so, I always joke, if he hadn't done so, he could have had a quite astounding career.
Hmm. How did all of this go back, though, to Georges Lemaitre, who you mentioned, and his primeval atom model for how the universe began, which I think is the predecessor or precursor of the Big Bang?
Yeah. So in 1927 through 1932, Lemaitre worked on this model of a consequence of Einstein's general relativity, showing that the universe, if it had matter in it, would be unstable. And if you didn't have this cosmological constant, for which there was no evidence until the 1990s, so based on what they knew back then, there was no evidence to support this. And even by 1927, there started to accumulate a great deal of evidence that there were other wanderers in the night sky. And these included what were formerly called spiral nebulae, which were thought to be part of the Milky Way galaxy until 1923, until Hubble discovered what's called a Cepheid variable in
Mm-hmm.
the galaxy that we now call Andromeda, but it used to be called the Great Spiral Nebula in the constellation Andromeda. They thought it was just in the Milky Way galaxy. Then they realized it was far outside the boundary of the Milky Way, so it had to be external to the Milky Way, and they called it an island universe. So you have to put yourself in the mindset of the person in the early 1920s. You've gone 1,900 years thinking that the universe was static and it only had 5 things that moved in it. Now you realize that not only is the universe not our solar system, it's not even our galaxy. And so they called other galaxies island universes. So once this was discovered, it was then discovered that the Andromeda galaxy wasn't the only one of these nebula. And a scientist by the name of Vesto Slipher, I'd love to know the
Great
origin
name.
of Vesto. Yes, that's right. So good old Vesto, he and colleagues made a survey of these spiral nebulae. And they actually did this before 1923. So they didn't know what these things were, that they were external to the Milky Way's boundary. And Vesto observed that about 19 of 24 or 25 of these nebulae had a peculiar property, that they had observed in them stars, and every star is an incandescent glowing nuclear ball of fusion. And that glowing ball of nuclear fusion has characteristic spectral lines, the chemical fingerprint bespeaking of its composition. So stars are mostly made of hydrogen. They fuse hydrogen to make helium. That's where we get the term helium from. It means sun. And that's because it was discovered not on Earth, but it was discovered on the sun. I don't know if you knew that, but helium was discovered on the sun. Yeah. So they had to go at night to observe it. So helium was first observed, and then it has characteristic spectral lines indicative of the electronic transport within the atom. And that's driven by photoelectric interactions and quantum mechanical processes. But it can be used to make a chemical fingerprint, and that chemical fingerprint had a different behavior depending on this particular galaxy's distance from the Milky Way. They all, with the exception of about 5 of them, they all showed a characteristic fingerprint. So if you're listening, I'm holding up my hand. They all showed it shifted to longer wavelengths or lower frequencies. That's called a redshift. And it's just the same phenomenon that you'll hear when an ambulance is moving away from you. You'll hear the pitch of its sirens decreasing. And that decreasing pitch then makes a characteristic imprint that can be used since Doppler's time in the 1700s to measure the velocity, the recessional velocity of an ambulance, of a train, or of a galaxy. Except that the galaxy, its velocity is measured relative to the speed of light, and for objects on Earth, it's relative to the speed of sound. So for the speed of light, these galaxies were receding at tremendous velocities. They were receding at fractions of the speed of light, which is incredible, with a handful of exceptions. There are about 5 out of the 23 or 24 sample size that he measured, that that Vestos-Slipher measured. And then what Hubble did was synthesize the data of Slipher showing recessional velocity, v. And then Hubble correlated that to distance measurements, which he knew how to do, courtesy of one of the most unsung heroes of astronomy named Henrietta Swan-Leavitt, who'd come up with a measuring tool to use the brightness of a variable star as an indicator proxy for its distance. And that's what Hubble put together and made a very simple but extremely bold plot that showed velocity as a linear function of distance away from the Milky Way. And like I said, there was only 1 or 5 handful of these galaxies out of, more than 2 dozen that showed a blue shift. In other words, they were coming towards us or they were static with respect to us. And of course, in later years, we've measured, the spectra of hundreds of millions of these objects, and all of them, except for those same original, 5 or 10, are moving away from us. So from this conclusion, Hubble and Slipher and Lemaitre began to draw a picture that the only way that this could happen, there are 2 ways this could happen. The Milky Way was indeed the center of the universe, and everything was moving away from us as if we had, some kind of cosmic body odor dysfunction. There was some problem with us, or that every galaxy is moving away from every other galaxy in an expanding 4-dimensional space-time. And it could have been that they were collapsing towards us or coming towards us, with a handful of exceptions perhaps, or it could have been that they were moving away from us, but it certainly wasn't the case that they were static. And faced with this, in 1927, when Lemaitre came up with this, again, there was only a very small set of data. By that time, Einstein rejected this notion of Lemaitre. He said famously, your math is correct, or your math may be correct, but your physics is atrocious. Meaning that how could you have an expanding universe? The implication was that if you ran the clock backwards in time enough, we would be touching not only these 24 galaxies, but we'd touch every single galaxy in the universe, and all the matter in the universe would be concentrated in one spot, which is what Lemaitre called the primeval atom. He ascribed the observed amount of galaxies, he converted them to a typical mass, and he said if all of their mass was once in a certain compact region of space-time, they would only fill up a volume equal to a sphere of the diameter of our solar system. And they would have nuclear density at that point, and maybe even greater than nuclear density. So they would have atomic nuclear density. That's what he called the primeval atom. He realized that was unstable, that would explode. Nowadays, we don't view that as the correct picture, but there is still no certainty as to how that picture arose in the first place. So that was the primeval atom. Einstein rejected it until 1929. By 1929, Hubble had plotted his famous law. And by the 1930s, Einstein visited Hubble down here in Southern California, Mount Wilson, and was convinced that he had made a mistake in assuming that the universe was static. And actually, so therefore, his model of a static universe was disproven by observational data, acquired by telescopes built by instrumental builders, experimentalists, and but it wasn't that the Big Bang was proven. In fact, we still don't know if the Big Bang is proven in the conceptualization that Lemaitre had. So that shows you what we do as physicists. We don't prove, we falsify. And so Einstein's static universe model was clearly falsified. And then that brought in, as typically happens in science, as you know, once you patch flaws in an existing paradigm, new flaws and new cracks emerge. And later on, we'll get into inflation, and inflation purports to patch many of those lacunae in the original Big Bang model.
Mm-hmm. Well, that was a great summary. But first, before we move on, a few comments. One, that's the the first time I've ever heard actually the cosmic body odor hypothesis for expansion. It would be really nice if
Also
that
fine
one
with
were true. Yeah. But another thing you mentioned island universes, and of course, island universes have come back into the picture in the past, I don't know, 30 years or so in the form of the multiverse. And I was talking to, not on the show, but I was talking to Andre Linda here
yeah.
recently, and he mentioned your episode with him on inflation. And am I right that you've also spoken to Alan Guth as well in
I
Into the
have not.
Impossible?
I have.
You haven't? Okay.
I have a. I mean, I'm friends with Alan. We've spent
Right.
dinners together. Um, he's atrociously, famously atrocious at replying to emails. So I'm hoping to be at MIT in the next year. So I'll pigeonhole him in his office. But yeah, we're cordial, and I'd love to have him on the podcast.
Yeah, that would be great. I mean, he's an important character in losing the Nobel Prize. But moving more toward the thread that we were just discussing, you mentioned that the static universe conception had basically been around for 1900 years, and even Einstein, as you mentioned, due to philosophical prejudices or aesthetic intuitions, one of the greatest geniuses of all time, he resisted the notion of an expanding universe. And of course, I mean, various iterations of the static universe have been the dominant opposition to the Big Bang model ever since its inception. And even after the discovery of the cosmic microwave background, as you mentioned, I just spoke with John Mather, the who obviously the Nobel laureate who was with George Smoot in basically in charge of COBE. But um, yesterday, and of course, there remain plenty of questions about the Big Bang, as you just mentioned. Yesterday, when I was talking to Juan Maldacena, he mentioned that it's one of the most interesting questions to him that M theory is working toward. But aside from, I guess the obvious lingering question, what was before the Big Bang, or what started it? What were the biggest problems, or what have historically been the biggest problems that led to Alan Guth and Andre Linde and the inflationary hypothesis?
Well, for Alan Guth, I think it was imminent unemployment. I think that was the inciting incident for him. He was at your fine institution on Sand Hill Road at SLAC, Stanford Linear Accelerator Center. His postdoc was coming to an end. He had a newborn, a young wife, in 1979, and he was, ruminating on many different problems. And one of the problems had been kind of proposed to him by a very famous, but really largely unsung hero of modern physics, not just theoretical, cosmology, but really of all physics. And that's a man by the name of Robert Dicke, who
Hmm.
co-invented radar. He co-invented the lock-in amplifier, which you can buy on again across the street from you at Stanford Research Systems. They sell them for about $40,000 now. Inflation is a wild beast, and not just a cosmological kind. When I was your age, they were about 12K. Anyway, these technologies that he invented allowed us to win the war, and he invented the microwave radiometer, and he also was predicted the temperature of the CMB, forgot about it for 20 years, tried to measure it, and then got scooped by Penzias and Wilson, and famously said it, "Boys, we've been scooped," to some
Right.
past and future guests that I've had on the podcast, including my PhD grant advisor, David Wilkinson. So, so Dickey had been thinking about these weird kind of numerological coincidences in physics. And one of the dirty secrets of science and physics, especially, is that we have some common bedfellows with astrology, in the case of astronomy, with alchemy in the case of high energy particle physics, and
Hmm.
in some cases with numerology. And so there were a lot of strange numerical features of the universe. And Dickey was right to point these out. And I believe that Guth heard about this coincidence that the what's called the density of the universe and its concomitant geometry are very close to flat and very close to what's called the critical energy density, meaning that any triangle that you make on cosmic scales will have interior angles that sum to 180 degrees. That's all it means. And so it could be otherwise, but it's very peculiar. that value, right? Because there are two other global classes of curvature: positive curved spheres and negatively curved hyperboloids or Pringle chips. And there's an infinite number of each one of those. There's only one with perfectly flat geometry, like Euclid would presuppose. So Dickey pointed out that it could be that the universe is open or closed back in the late 1970s. They didn't know. Now we know it's precisely flat with an error on the precision of it, rather, of about 0.3%. In other words, it could only be maximally positively curved or negatively curved by a third of a percent. It's incredible what my colleagues have done. But back then it was unknown within a factor of 2 or 3, but yet it was very close to this flat number. And Dickey said that's a strange coincidence that needs to be explained, and we couldn't explain it in the standard Big Bang model. It was just had to be put in by fiat. So Guth heard about this, knew about this, and set off to think about this. But he was working, as I said, at SLAC, which is a particle accelerator, which is a weird place for a cosmologist, but there are still many, many of my friends hopefully listening here. I'll give a shout out to them at Stanford and SLAC, and they work on smashing atoms and and electrons and subatomic particles. So he was focused at one point on what's called the missing monopole problem. And the missing monopole problem is that in most theories of the extreme cosmic baby picture, there were phase transitions in between the four forces of nature that, upon their breaking, lead to defects in that are of a topological nature that go by different names. But the simplest one is called a magnetic monopole, which is exactly like an electron or a proton, and that has a single unit of magnetic charge, very much unlike any magnet you've ever encountered, which even if you break a horseshoe magnet in two, you don't get a north pole and a south pole. You get two north poles and two south, north and south, and north and south. Mm-hmm. So why is that? Why don't we observe a single isolated north pole? It's very bizarre, and it's part of Maxwell's equation. So the issue that they tried to kind of understand was, why don't we observe these? And Guth, working on the missing monopole problem, realized that if the universe had undergone an extreme period of expansion early on in its history, after the phase transition that could have nucleated these monopoles, then it would be very unlikely to ever encounter one in our observable universe. And that remained true until 1984, I believe, also at Stanford. Blas Cabrera, who's a wonderful scientist and friend, he claimed that he detected the monopole in our universe on Valentine's Day. I have a video about that on my channel. And it turned out not to be verifiable because maybe it was just one monopole, maybe he was right. But nevertheless, it again wasn't proof of a theory of inflation or extreme cosmic expansion, but it was evidence, or it was consistent with a model that had diluted and diffused the universe by exponential amounts. And that led Guth, as I understand it, along with this flatness paradox, to conjecture a mechanism by which the universe would instantiate those two phenomena: a flatness on large spatial scales, or near flatness, and a absence of magnetic monopoles. And later it would be shown to have many other virtuous features as well, and leading to its sustained popularity for the last 44 years. It's just incredible. But again, lack of proof, but tremendous circumstantial support for it.
Tell me if you think that I'm wrong here. Maybe this isn't generally true, but the way that you speak about the theory and the depth with which you understand the history, and I mean, we just skipped over a lot of history about Hoyle, Gold, Bondi, this back and forth between steady state and Big Bang. But what all this suggests to me is that what I think is a common belief about astronomy and astrophysics from outsiders, it's one that I once held, that there's a major gulf between theorists and experimentalists or observers. They're siloed from one another, is completely wrong. And you're, in fact, very closely working with theorists. You're well informed by theory, and they're very invested in what's going on with experimentation. So, for instance, Maldacena yesterday mentioned your work in BICEP and BICEP 2 when we were talking about the CMB and string
Yeah,
theory.
it's certainly true. And I think I think there are multiple aspects of what you just said. One is that there is maybe possibly justifiable perception of a tension between theorists and experimentalists. You want that. You want checks and balances. You don't want, an experimental team looking for inflation, although that's what I invented with BICEP. Um, and looking back, I wouldn't change a thing. But the notion that I was going to win a Nobel Prize by detecting waves of gravity and therefore justifying inflation, that no longer, has the same appeal to me, or it no longer animates me as a man, as a scientist, as a human being. I'm very curious about it. But to think that, I'm going to prove this right. And then I always felt like, there's a joke, what do you call a guy who hangs out with musicians? You call him a drummer. And I always thought, like, sometimes there's a perception in theory that the theoretical physics is the crown jewel of all of science. So when you think of the greatest minds of all time, you think of Feynman, you think of Dirac, you think of Einstein. What do all these guys have in common? Maria Mayer. I'll throw in a woman here from UCSD's past history. Um, you see that they're all theoretical physicists. So what gives? So is the joke to be, what do you call someone who hangs out with physicists? You call them an experimentalist. I actually think experimentalist, and what made Dickey so remarkable is that he was an experimentalist and a theorist. He made tremendous contributions to the understanding of cosmology, of particle physics, of gravity physics, and yet he was an experimentalist that built the first radar sets and Lock-in amplifiers and microwave radiometers to measure the cosmic background. He is my kind of modern day hero, the way that Galileo is my ancient hero. Galileo used theoretical methods and models to predict what he would see. And then he built a telescope, or he built a ramp with an inclined plane, or he built a pendulum, or he tried to build a virtual reality helmet. He did so much in experiment. And I think we need more like that because, we have joked like we don't let theorists into the lab because something always goes wrong when they come in. And some of my best friends are theorists. I love them, and I've collaborated with them. So my motto for my graduate students, if you were working in my lab, I would say you have to understand theory as well as the graduate student that you enter, UCSD with or Stanford with. But unlike him or her, your job is not to come up with new theories, but you must understand it. Otherwise, no offense intended to plumbers and electricians, but you're just quote unquote a technician. In other words, you should be doing something else that you'll get more highly remunerated for, because being a graduate student, as you know, doesn't pay very well. So why are you doing this if you're not curious about the underlying implications of the data that your instrument collects, namely what theories can it kill off? And so I always tell my students that. And I have had theoretical graduates that do theory, and they do have to come up with new theories or new analysis methodologies or phenomenology. But that's, one out of every five of my students is a theorist. So that's my philosophy, that a good physicist as an experimentalist should know theory like a good beginning graduate student in theory, but build experiments to test and prove his friends wrong.
Hmm. There's a similar relationship within philosophy in that a philosopher of physics like David Albert. Well, David is a physicist, so it's a little different, but there are other physicists, philosophers of physics who don't have a PhD in physics, but they need to know the physics very well if they want to sort of kill off interpretations of quantum mechanics, for
Yeah,
instance.
and that's I hope you'll put me in touch with David. You're talking to him again. You said, right?
Yeah, yeah, yeah.
So one of the things that I'd love to talk to him about, and so please don't steal this question because I would love to talk to him about it, is I've had on many times Lawrence Krauss on my podcast. And oftentimes, Lawrence and I have spoken about, topics ranging from, Judaism to the meaning of life to climate change. But we've also talked about his famous, book, A Universe from Nothing, which was very, very critically panned, I believe, in the New York Times Book Review by David Albert, 10 years ago when it came out or more. And I'd love to kind of, get David's reaction to some of the things that Lawrence has said about him and philosophy. because there is a tension. There is a kind of pedantic, a snide, often, how can I put it? Often, kind of churlish attitude between real physicists and philosophers. And
Mm-hmm.
that's, philosophy has done nothing, to create new knowledge. It was useful during the time before we had electron microscopes and MRIs and 12-meter class telescopes, but it no longer is a vital source of, nobody goes and thinks about the categorical imperative and decides on how they're going to raise their kids, even, so let alone the philosophy of physics. Now, David was, of course, not merely a philosopher, as Lawrence kind of, in my opinion, slightly, tongue in cheek, maybe, but disingenuously criticized his review of his book. And, maybe Lawrence has too thin a skin. I don't know. I'm doing a live event with him on October 17th. Depending on when you're listening to this episode, please come to the San Diego Air and Space Museum, me and Lawrence in conversation. And I could put this to him. Hopefully I'll talk to David before that. But there is an uneasy, relationship, but I think it's only one way, right? Correct me if I'm wrong, Robinson, but you don't look at physicists and say, oh, you guys are too materialistic. You got not material, like in terms of materialism, not like in terms of the Hermes, shirt that I'm wearing right now. But tell me, is there a corresponding, kind of a negative attitude? I don't sense there is, but I could be wrong.
I am a bit distant from the philosophy of physics community, but I certainly think that there is some resentment and some belief that it's really an arbitrary and sort of wrong decision to not have foundations of physics, for instance, within a physics department. And so I think in that respect, some philosophers of physics might feel negatively about physicists because they think that they aren't sufficiently interested in important physical questions.
I see. Okay. Interesting. But I mean, I guess, yeah, Lawrence and Neil deGrasse Tyson and others of that ilk have spoken pejoratively, I would say, more than it's warranted. I personally feel
Yeah.
philosophy is fascinating and worthy of study. Although I had my one and only philosophy class at Case Western, which was administered by a professor who gave 100 question true or false quizzes. And I somehow, Robinson, managed to score like a 34% on all the midterms. I thought I was going to fail, end up getting a B. I don't know how that's possible, true and false, but it's pretty wrapped up to have philosophy tests like that. But yeah, getting back to the original thread, I think it is, kind of, it may date back to my hero Galileo. Galileo used to talk about his discoveries as killing off the work of what he called, philosophers. But I think what he would say is, so he observed like the Pleiades asterism, and in it he said that this was evidence that they were made of stars and not some strange new substance, quintessence or something. And he famously said, "I've thereby observed the nature or matter of the Milky Way galaxy, which has for generations vexed philosophers with their wordy claims." And but I point out, like these, Galileo thought of himself as a philosopher. It's called a natural philosopher. And nowadays we have modern incarnations in the form of Sean Carroll, who's a professor of natural philosophy at Johns Hopkins now. Another good person to get to know if you haven't. And yeah, so now I think we're kind of returning to the hopefully less uneasy peace that used to exist between philosophy and
Mm-hmm. Yeah, Sean has been on the show a number of times, and he's a great person to talk to. I really enjoy talking to him. But just one aside before we get back to the other thread, and that was I play the drums, and what's funny is that I don't feel like a musician. I feel like more of a technician, to use another word you mentioned. But anyways, so detecting gravity waves to verify inflation. Where does polarization fit into this? And why does detecting gravity waves, why would that have verified inflation? What I'm aiming towards is your baby BICEP, which I'd really like to get to.
So in 1997 or 8 or so, let me take a step back. In the early 80s, there were many physicists who speculated on the properties of the cosmic microwave background, which had only been recently detected in 1965, and whose spectral properties, which are the easiest to measure because it's much easier to measure something that's 3 Kelvin, as hard as that is to measure, and something that's a millionth of a Kelvin, like the polarization or anisotropy of the microwave. And immediately in the discovery announcement of Penzias and Wilson in 1965, they announced to their level of sensitivity the CMB radiation, which bathes us in all directions as if we're inside of an oven, because in the sense we are. Luckily, that oven is only 3 Kelvin. And that is a consequence of the aftermath of the formation of the first atoms, which formed. There were searches in that very paper in 1965, which was only like one-page paper, which might be the shortest ratio of Nobel Prize to paper length, and they ended up stating that to their sensitivity, they could not discern any anisotropy. In other words, it looked perfectly homogeneous isotropic, nor could they discern any polarization. And that's because the properties of a distribution of photons only has three properties. It has a characteristic spectrum, it has its isotropy or smoothness as viewed in angle, and it has its polarization. Those are the three properties of an electromagnetic wave: frequency, intensity as a function of position, and polarization. That's it. Every other fungible property is completely interchangeable.
Since the polarization of light hasn't come up on the show before, I think it would be worth, since it's going to be very important in a few minutes, just explaining what this is.
Yes. So light has three properties. It's a spectrum. It's a rainbow of colors. It's intensity as a function of wavelength. It has its overall magnitude or amplitude of its intensity, how strongly oscillating is the electromagnetic field in a given direction at a given wavelength. And then the direction in which the electromagnetic field oscillates is called its polarization.
Hmm.
And in fact, it's the electric field. So the electric field determines the polarization. It's just like two people swinging a rope back and forth in a jump rope. The plane that the wave is oscillating in, the rope is oscillating, is called its polarization.
Okay, great.
So, and whenever light, polarized or not, interacts with matter, any kind of matter, there is a probability, in fact, of that light becoming more or less polarized. So if you have a 0% polarized object, like the sun is a pure black body. It's highly anisotropic, that's only in 1/2 a degree wide spot on the sky. But the light is coming as if it's a perfectly random Brownian distribution, almost of the direction of photon oscillation passes, 100% unpolarized. And yet, if you have the resources, you should always buy polarized sunglasses. Why? Why should you buy polarized sunglasses if the sun is unpolarized? Well, that's because the sunlight that we see is not only coming directly from the sun, and take it from me as your friendly neighborhood astrophysicist, do not look at the sun with your remaining good eye. But when sunlight bounces off the surface of the ocean or off another dielectric like the ground or a road, it becomes partially and sometimes completely polarized. By suppression, there are only two polarization states of light: vertical, where the plane is oscillating vertically, or horizontally. And then every other combination can be a superposition of some amount of vertical, some amount of horizontal. You can get any angle of any plane of polarization you like. But unpolarized light is completely without any given direction. But when it interacts with the ocean or the land, it becomes possibly highly polarized. That allows your sunglasses to block with a filter, like a picket fence that only allows one direction of light to come through. And in the case of sunglasses, it will be vertically polarized to block, because the light that's getting scattered will be primarily horizontally polarized. So you'll be able to see through the surface of the ocean or the lake or whatever that you're fishing. So polarization results from the interaction of unpolarized light with matter. So now go back to the early universe. There wasn't an
Mhm.
ocean, there wasn't a pond, there wasn't a road, but there was a lot of matter in the form of electrons. Those electrons were present from the earliest phases of the Big Bang. And in fact, there are protons present too, and they only combine together to make the first atoms 380,000 years after the Big Bang. That's called recombination, and that's when the CMB is produced. And so the light of the CMB can be partially polarized. It's actually very weakly polarized, but it's polarized because the light that was present, that was unpolarized heat, interacted with matter that had an anisotropic distribution. So the polarization we see, it results from the imperfections in the distribution of matter and the properties of the earliest light left over from the fusion of the first electrons and protons to make hydrogen. That process can be influenced, the anisotropic imprinting in the early matter plasma can be accomplished in many ways, one of which is if there was a background at that time of gravitational radiation, gravitational waves.
Hmm.
The term gravity waves should be deprecated. That as a specific connotation in the theory of fluid mechanics. I don't care if you use it. I sometimes will use it, but a real persnickety professor on your candidacy exam might say, hold on, he doesn't know what he's talking about. He called the gravitational wave a gravity wave. Be that as it may. Gravitational radiation, if it's present at the earliest moments of our universe's fusion of the elements to make the first atoms, that process will imprint an anisotropy in the primordial plasma, which has a telltale pattern when observed today, one that we call B-mode polarization. I realized, thanks to the work of collaborators like Matthias Zaldariaga and Uro Seljak, and folks like Mark Kamiankowski, Arthur Kozowski, and others, that there would be a specific pattern that could be measurable. And this all dates back actually to a Russian colleague and mentor of mine named Alex Polnarev in the 1980s, who predicted what a single wave of gravitational wave, would do to the polarization of the cosmic microwave background. Then this was updated, modernized, translated into language an experimentalist can understand and search for. And I realized that the technology had come a long way by the year 2000, that we could finally build a camera, a telescope of the Galilean sort dedicated to measuring the specific telltale fingerprint of gravitational waves. Where do the gravitational waves come from? There's only one way that we believe we can get a stochastic random background of gravitational waves, and that's if the universe had a period of exponential inflation prior to the formation of the elements and their nuclei, and that's called inflation.
So then, just to reiterate, in a simplified fashion, if you could detect B-mode polarization in the CMB, that would indicate the existence of primordial gravity waves in the early universe at the time of inflation, and that would get a Nobel Prize.
That syllogism is about as good as I've ever heard it described.
Okay, perfect. So then, I think if I'm not mistaken, you came up with the idea for BICEP when you were at Stanford, or did it come out of some ideas from your time at Brown?
Well, my thesis at Brown was to build a microwave telescope that could only see the largest possible scales on the sky. Its resolution is very coarse. It was actually made from discarded parts from the Kobe experiment that John Mather and George Smoot had graciously loaned or given to my grand advisor, David Wilkinson, who gave to my advisor, Peter Timby. And then we built this radiometer out of the spare parts of an instrument that would later win a Nobel Prize, basically. So that pedigree is kind of cool. So I built that instrument. Then I was hired to work on a different project at Stanford by Professor Sarah Church, who's still there. And she is in the physics department, and she was a brand new first-year assistant professor there. And she hired me to work on specific telescope in Hawaii, and then to start building parts for a telescope in Bishop, California, Owens Valley, and other things. And I was, quite frankly, a pretty bad employee. I was prone to distraction, to look up things that was more interesting intellectually to me than working on what she wanted and hired me to work on. To give myself some solace, or perhaps to give myself some flexibility or opportunity for repentance. I was making $32,000 a year, which is probably less than you make. It was 1999, the height of the dot-com boom. I lived on the train tracks near Alma Street up there. And every 15 minutes, a Caltrain would go by from 5 a.m. to 1 in the morning, shuttling folks between the Bay Area and the Silicon Valley up to San Francisco, where all the startups were. So I was going on very little sleep. I was a very much disagreeable. And like I said, I was a pretty poor employee. But the one thing that kept me up was I wanted to do these really big, swing for the fences. And the projects I was working on with Professor Church were, in my opinion, very interesting, very important, but they weren't going to break the ground of discovery of something akin to discovering what caused the Big Bang to bang. And so I was fascinated by that. I'd read a paper by my friend and later colleague, Mark Kamienkowski, and Arthur Kozowski, and Andrew Jaffe, and others, um, making note of a very simple fact. They made a note of it, but they didn't realize the implications, I don't think. They basically showed that the size of a telescope was almost irrelevant in terms of its sensitivity to waves of gravity, which would then probe inflation. And at that time, as is the case now, astronomers have what's called aperture fever. Since I was 12 years old and got my first telescope, I've always wanted my next telescope. And as they've rumored, to say, I think J.P. Morgan was once asked, how much money should a person strive for? And he said something like, just a little bit more. And and astronomers feel that way about their telescopes. How big should your telescope be? Just a little bit bigger. And so there was like an arms race of building ever increasing telescopes. In fact, there was a plan to build a telescope at the South Pole. Now, be 10 meters in diameter. My telescope that I built for my PhD thesis was 10 centimeters in diameter. And the telescope's collecting power scales as the area of the telescope aperture, but its cost scales as the volume, the cube of the aperture diameter. So these telescopes are getting to be just incredibly expensive. And I thought, well, if you wanted to build a very nimble instrument that was only capable of seeing waves of gravity from the incipient inflationary birth pangs of the Big Bang, you would need only a telescope about a foot or 2 feet in diameter, which is basically free. And so I spent most of my time thinking about that instead of doing what Professor Church rightfully expected of me. And so one day, it was actually precipitated by the visit by Jill Tarter, who is still a friend and a mentor to me and millions around the world, at the SETI Institute at the time. She came to give a talk. I asked Sarah Church to get me an invitation to go see her at the colloquium dinner. And Sarah told me it's not my job to get dinner for my postdocs. And I always remember thinking, well, all right, she's on to me. She's seen I'm a slacker. I'm not doing what she wants me to do. And then soon thereafter, I was fired. She actually said, I don't think we have a place for you here anymore. We want you to leave. I want you to leave. But she did me, perhaps the greatest favor in my history, which is that she arranged an interview for me with one of the most magnanimous personalities in all of cosmology, Professor Andrew Lang at Caltech. And he was a legend already in the time. He was tall, dark, handsome, incredibly successful, had been stolen from Berkeley at great cost. He recruited his superstar wife, Frances Arnold, partner. She would go on to win the Nobel Prize in 2018 in chemistry. They were the power couple of all power couples. And he was gracious enough. He invited me down to give a seminar, and I did. And he offered me a job. And before he finished the sentence, I accepted it because to work for him meant that I would be changing locations, changing situations, getting out of a place where I wasn't wanted anyway, rightfully so. And so I moved down to Pasadena. And as soon as I arrived in Pasadena, I kept pushing this idea of building this instrument to Andrew Lang and my friend Jamie Bach, who's currently a professor at Caltech. And Jamie and I would play tennis every Wednesday night, rather. And one day I just kind of mentioned it to him. He thought, what are you working on? I said, I have this idea. We could build a very small telescope that could actually be the first dedicated instrument to measure inflationary gravitational. And he said, oh, that's interesting. And he brought it to Andrew, and Andrew basically said, let's do it. And so we applied for money. David Baltimore was the president of Caltech. He had $1 million discretionary fund. He gave it to Andrew and Jamie and I. We started building BICEP. In the first instance of BICEP, which would be a telescope located at the South Pole, a refracting Galilean telescope that could only measure waves of gravity. And in fact, in 2014, we claimed that we did measure those waves of gravity with a successor instrument called BICEP 2, which is just like your iPhone 15. It just has more pixels, it has higher sensitivity, but the same basic idea as the iPhone 14. BICEP 2 is basically essentially the same cryostat, same location, same optics design, but with better, more sensitive and more detectors. And so we claimed in March of 2014 that we had measured the imprimatur of inflation, these B-mode polarization pattern, uniquely indicative of gravitational radiation itself, as you summarized so beautifully, indicative of evidence for, not proof, but at least very strong circumstantial evidence for inflation.
Well, a few things. One, speaking of aperture fever, I just heard an episode a few weeks ago that Sean Carroll put out where he was talking to a physicist who wants to put and I'm sure lots of people want to do this, but put a telescope on the moon that has a diameter that's like the size of some massive crater. So aperture fever is a very real thing. And then speaking of Andrew Lang, I mean, he was a very magnetic character in your book, and it was touching. I mean, I just read it. I know this was many years ago, but it is a tragedy that his life ended as it did. Very unfortunate.
Yeah.
But going back just to BICEP, I've been hearing about your tale in the South Pole, and your writing about the early Antarctic explorers. It was all terrific. But I'd like to talk about the telescope itself. Two of the most enjoyable aspects of episodes on the podcast so far have been talking to Carl Wyman here about his experimental design when he isolated the first Bose-Einstein condensate, and then John Mather with COBE. So I'd really like to get a bit into BICEP. So maybe we should start with, what are the essential components of a polarimeter?
So a polarimeter could be built from the polarized sunglasses in your eyeball, in that it requires basically only two different, maybe three different components. It needs a polarizing filter that selects one of the two polarization states, either vertical or horizontal, and that's given by the polarized sunglasses. And then your eyeball is a little refracting telescope. It has a lens and it has a detector called your retina. And those, if they're not polarization sensitive, there's a tiny bit of polarization sensitivity. We're not going to get into that. But the combination of your eyeball and polarized sunglasses makes a polarimeter. So it's something that selects or filters out one of the two polarization states of light. And then to verify that the light is polarized, you need only modulate or rotate the polarimeter about its axis of symmetry. So for your eye, you'll be rotating about the center of your cornea while keeping the polarized sunglasses on your eyes. And then if you look at the sun, again, if you look at a cloudy day, cloudy, you will see no modulation as you rotate your eyes around, or you should not see it, depending on where you look. There could be a slight polarimeter, but for all intents and purposes. On the other hand, if you look at sunset and you look directly at the zenith, wearing polarized sunglasses, totally safe, and you spin around, you'll see the intensity of the skylight that comes to your eye modulating twice every time you spin around about the vertical. That is because a polarized wave only has a plane in which it's oscillating. It's essentially a type of one form. And so as you modulate, you can't tell if the electric field is pointing up or down. You can only tell it's in the up-down plane. And so it will go around twice for every physical rotation of once. So we built a polarimeter that would do that. And we did it. It had microwave detectors in it, made of very, very highly engineered detectors made by Jamie Bach's team. at JPL, either superconductors or semiconductor bolometers. Those, unlike your eyeball, in order to operate and detect the 3 Kelvin signal that has a potential 1 nanokelvin's polarized component riding on top of it, that detector system has to be cooled near to absolute zero. So actually, BICEP is effectively the coldest telescope in the entire universe, or at
Hmm.
least it was until JWST. I think has a slightly colder instrument, but it may not. It may still be, and that is because the entire telescope, the detectors are cooled below the temperature of interstellar space. So they're cooled. The optics are cooled to the temperature of the microwave background by liquid helium.
2.7.
Yeah, they're cooled slightly above that, but the interstellar medium is, so essentially, 100 times, 10 times warmer than the detectors. So these detectors operate on what are called the superconducting transition edge, where a small change in incident energy will cause a large change in resistance, and that phenomenon is well known. And so we measure the intensity of the light by how much the superconductor's temperature is changing and its resistance is changing, which is easy to measure, relatively speaking. And then we modulate the telescope by rotating it around its axis. So it's very simple. It's a Galilean telescope. Take a spyglass, Galileo used or whatever, put your polarized sunglass on top of it, and you too have a polar image.
Hmm. And well, a couple of things. One, BICEP is among the, I don't know, it's probably the best acronym that there is for a telescope out there. What does it stand for?
So BICEP originally stood for background imaging of cosmic extragalactic polarization, which is pretty ironic because we ended up measuring galactic polarization with it. So it's a little bit of a misnomer.
Hmm. Okay, and then you already mentioned the extremely low temperatures to which BICEP was cooled, but that I don't think has anything to do with why it was in the South Pole, which is interesting in its own right. So why did you have to take it down there?
So principle of microwaves, and I'm trying to look for my recently microwave coffee, which I'll need to warm up in just a bit. So the reason your microwave oven works is that you heat up the water molecules inside this cup. I'm showing a cup of Dunkin' Donuts famous coffee. And the water molecules will start to vibrate and oscillate, and eventually they'll boil. But the cardboard or ceramic container does not, because it doesn't have any water in it. It's very dry. So the lesson is water absorbs from microwaves. Microwaves in this microwave oven are about the same wavelength as the microwaves in the CMB detected by Penzias and Wilson. So it's not at all, a done deal just because you build a microwave telescope, you'll be able to see something. Because we live on the surface of a planet that's highly watery, whose atmosphere contains a tremendous amount of water. From Earth, sea level to space, can contain in San Diego, which is a desert, coastal desert, we can still have, centimeters of what's called precipitable water vapor. So you want to go somewhere where there's low water vapor in the atmosphere, which typically means somewhere very cold or very high, or basically both, because you do not want this 13.8 billion year old photon, which may be slightly polarized in this curl fashion. By the way, bicep is the muscle that does curls at the gym, right? You look like you know that. You look like you go to the gym. You got a tattoo on your bicep. I'd love to see our bicep pattern, the telescope, beam of
Yeah.
polarization there. I would give you serious street cred. So the pattern of polarization indicative of gravitational waves, themselves indicative of inflation, has a curling, twisting component pattern to it that's unique, that's asymmetrical under reflections. So that was given the name by Mark Kaminkowski and Arthur Kozowski and others. And that curling pattern, I always like the name, is what BICEP is meant to do. So we did the heavy lifting of measuring curls. That's why the name has double meaning. So yes, so ultimately the measurement of this polarization pattern would be indicative of it, but you had to take it somewhere very dry, preferably outer space. But space costs 100 to 1,000 times more
Right.
to given kilogram of material or telescope. And in fact, some of the telescopes we're building now for the Simons Observatory are larger than any telescope that will be in space for many, many decades.
Hmm. Last night I was walking my dog around campus, and the stars were twinkling, and I thought, "Oh, twinkle, twinkle, little star." So maybe for 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 our listeners, just to make this a little, or bring it a little closer to home, the stars aren't actually twinkling, but we perceive them as twinkling because of atmospheric noise. And you were moving the telescope, or you located the telescope in the South Pole, not because of noise in the optical light spectrum, but in the microwave spectrum. And this is the last sort of background question I'll ask, but it's very relevant. Beyond noise in our atmosphere, what other sorts of noise were you worried about trying to detect the B mode polarization of the
So
background?
there's two types of effects or noise sources that all physicists, experimental physicists, worry about. One is statistical noise, random fluctuations in all measurements, the imprecise nature of any measurement done by any instrument, and that can be reduced. And then there are so-called systematic errors, errors in the instrument, errors due to the location of where the instrument is, either on Earth, which is emitting at thousands of times more energy than even at the South Pole than the faint fractions of a Kelvin signals we're trying to measure. And then we're also located within a galaxy that is not exactly pristine vantage point to view the cosmos at large outside the galaxy. So we try to overcome that. But the only way to overcome a systematic effect is to build another instrument or another experiment that is just focused only on the experimental defect or the situational, the site
Hmm.
defects pose, the systematic errors. And so we do that not by building a telescope and taking it out of the galaxy. That would be really cool. Maybe in a billion years we can do that. But that's next best thing is to do experiments at multiple different frequencies. And by noting the fact that the various sources of noise of the site of the system, either from the telescope walls of the camera, or the South Pole location, or the galactic emission, or emission from other galaxies in the line of sight back to the Big Bang, those sources can all be mitigated by dedicated instrumental components that are focused only on that source. And then the ultimate measurement, we don't get, our data do not come in and say, I'm a photon that came from a particle of hydrogen, an atom of hydrogen, or it doesn't come with a tag that says, I am a photon that came from the thermal emission from a dust grain in the Milky Way galaxy. Instead, we get a melange of a signal that is the combination of the instrument noise, the site noise, the galaxy's noise, the atmosphere's noise, extragalactic noise, and there's many, many noise sources. Fortunately, most of them have a very predictable electromagnetic spectral behavior. And so we benefit from that fact by essentially making measurements at multiple frequencies and then cutting out the measurements that are inconsistent with the signal that's from the cosmos alone. So we get a signal that is the following: the cosmic signal plus the noise signal. In this case, the dust was the primary component of contamination. And then we make a measurement only of the dust, measuring at high frequencies where dust emits brightest. And then we subtract the combined signal, C plus D, cosmic plus dust. We subtract dust only, D, and you're left with a cosmic signal plus a little bit of extra statistical noise.
I know that I've already been quite glowing about your book, but I'll just say a few things before we go on, since we have to skip over a lot of material, and this is for our listeners. One, I mean, it's extraordinarily well written. I've read a lot of popular science books, and this one you have a touch for language, Schlemazel included. And then, I mean, there's a lot of drama too, especially involving BICEP, BICEP 2, and the data release that, I mean, we don't have to get into. But a third thing is that it's also just a great an accessible overview of both the history of observational astronomy, starting with Galileo, but then also modern cosmology, as we've already talked about with the Big Bang, inflation, this sort of thing. But since we have to skip over a lot of that drama, I just wanted to cut to the point here and ask, I mean, what you ended up finding with BICEP and BICEP 2 and what you ended up not finding.
So what we tried to do, what we were really hoping to do, was to detect the, kind of unmistakable imprint of gravitational waves on the cosmic microwave background from the data that we acquired with BICEP. However, we all agreed the probability was as close to zero as one could imagine. And this is important to realize. This kind of speaks to what I was saying before, that our job is to disprove things, not to prove them. So in the context of experimental cosmology, we knew we could make a measurement with a given sensitivity level. That's all we could say. What the conclusions of that experiment are up to, the scientific community once there's a consensus behind the results being accurately confirmed. However, it could be the case, and it still could be the case, and it could have been the case even if we were right and won Nobel Prizes, that inflation took place, but it took place at an incredibly low energy scale that's effectively undetectable. So I guess you would say, ontologically speaking, a true fact about the universe is that inflation took place. God or Guy, whoever you want, gives you a letter. Inflation took place, but doesn't tell you anything about how energetic that process was. So it could have occurred, and it could have made such a weak imprint on the microwave background that no experiment ever will be able to detect even the waves of gravity, which would, quote unquote, only be confirmation evidence, but not proof of the Big Bang originating in an inflationary epoch. So we knew that. We also thought it was just highly improbable. Out of all the values the universe could have chosen for the energy scale of inflation, there's a very narrow range between detectable or not, and certainly detectable by a human-made instrument, with year 2000 era technology. So we started it. We thought, we might see something, we might not see something. It was worth it. It was very high reward, and it was very low risk. When we ended up seeing a signal of curling, twisting B-mode polarization with BICEP 2, the successor instrument to BICEP 1 that I had invented and co-created with Jamie and Andrew, that instrument saw this signal that was exactly what inflation would have predicted. And for a while, many of us were very, very nervous. We weren't just excited that we had made this discovery and that we were straight to the printing press, although that's eventually what happened. We spent many months trying to prove that we had made a mistake, or prove that we had not made a mistake. You can actually do that. You can prove that the instrument is unbiased in a certain level. And the biggest source of uncertainty that we knew existed was the fact that we live inside of a galaxy, and that galaxy has dust within it.
Mm-hmm.
And the Milky Way has a magnetic field in it. And the dust grains are slightly magnetized, and they can get aligned by the Milky Way's magnetic field. And it's possible they could present the exact same type of signal that we observed with BICEP. And so this is in late 2013. We had, unambiguous evidence that the universe, that our measurements showed this B-mode polarization. And then we tried very hard to prove that it was not from inflation. And we found that we couldn't do it with the data that were available publicly at the time. So there was even an event where we tried to get data that weren't public, from the Planck satellite experiment, a €1 billion project that had been launched around the same time as BICEP 2 got fielded. And it was orbiting 1 million miles from the Earth, measuring the CMB's polarization as well. And they had also hoped to discover the signal if it was real. And they could have discovered it if the signal was as real as we thought it was. And so we had this predicament. The data that we needed, exculpatory evidence to exclude dust as the culprit for the signal that we knew we had, was only possessed by our number one chief rival, the Planck team. And even though Jamie Bach was a very, very key member of the Planck experiment, Andrew Lang, as you mentioned, had died by suicide or committed suicide, 4 years before, tragically. But he was one of the U.S. co-PIs of it. But Jamie built the detectors for Planck, so I figured surely he can get a peek at the data, but he didn't. He's a good scientist with great integrity. And so we didn't actually know what they had, and we asked them for the data. They refused to share it with us. They didn't have to. In retrospect, a lot of surus, as Yiddish would say, a lot of trouble and strain could have been alleviated had they done that, but they didn't want to do it, maybe because they thought they could detect the signal, or they just didn't want to, cooperate with us for whatever reason. And so we relied at one point on modeling of the signal, very exquisite modeling. And then at one point, they had given a public lecture where they had shown a PowerPoint slide that showed the data for dust only in our region of the galaxy that we had measured, or the sky that we had measured from BICEP at the South Pole. And that was just too irresistible for some people on the team. And we ended up making one of the 6 or so models that we used to exclude dust and galactic contamination was this, I joke, pilfered Planck plot from PowerPoint, where we basically scraped the data, made our own estimation of the signal, and then used it as, internally. And actually, in the very first iteration of the paper, we mentioned it as well. And it's just the ultimate confirmation bias. It's exactly what Galileo was suspect to, and Einstein was subject to this. I mean, it's one of the most pernicious forces in all of science. It's a hell of a drug. I've got a series of short videos on my channel coming up about confirmation bias, from Darwin to Wegener to all sorts of other people: Einstein, Galileo, and Carl Sagan.
Wegener, the psychologist?
No, Wegener, the originator of plate tectonic or continental drift. So, and confirmation bias can be good in the sense that ultimately there were say with Galileo claimed that the Earth orbited around the sun, which is true, but the evidence that he succumbed to confirmation bias on was the behavior of the tides on the Earth, which have nothing to say about the origin or the rotation of the Earth around the sun, revolution of the Earth around the sun. Anyway, so we had this predicament. We decided to publish anyway. And not only publish it, we didn't really publish it. We went straight to a press conference. This was organized by John Kovac at Harvard, Xiaolin Kuo, who's at Stanford still, Jamie Bach, Clem Pryke, and they also had Mark Kamiankowski, my good old friend, who had really kicked this all off, but I wasn't invited to this press conference. I'd been really summarily dismissed from the collaboration effectively after the death of Andrew Lang, who had been kind of a champion for my participation in the series of instruments that I had created. But after his death in 2010, I really didn't have such a champion, and the desire to share credit with me was non-existent among the 4 remaining PIs of the project. So they had a press conference at Harvard, and it was introduced by none other than Avi Loeb. And actually, 2 weeks before that, Xiaolin Kuo had recorded secretly a stealth video of him going up to Andre Linde's house and meeting with Professor Kalosh and Professor Linde and telling him that we did it. We detected inflation with this very large value, R equals 0.2. And he's like teared in his eyes because he knows at that moment that he's very likely to win a Nobel Prize. Mm-hmm. And that video got 2 or 3 million views in a day. And it was shared around the world. CNN covered the press conference eventually. And there was a rift between Caltech and Stanford about who's trying to claim credit for what at one point. A lot of politics in science that most lay people don't really have awareness about. Anyway, we announced it, and then within hours, people were trying to attack it, as we knew they would. We eventually put it on the archive, which is an open source, open access place to put articles that are going to be submitted to a journal. And then we eventually did get it published months later, 3 months later, I believe in July. And between July and March, when we had announced it, at the press conference, there were already claims that we had made a mistake, that what we had seen was not evidence for inflation, but only evidence for dust in the galaxy or synchrotron emission or galactic emission. Or some people said it was evidence for cosmic strings. Some people said it was evidence for magnetic fields in the early universe. It created, 800, spawned 1,000 papers in a series of a couple of months. And this really proves that this people make fun of me, or they object to the title. They say, you can't lose a Nobel Prize. You either have a Nobel Prize or you don't have a Nobel Prize. That's totally nonsense. Like you can't lose the World Series. You have to win the World Series in order to lose. It's preposterous. And not only that, but there are many people who have lost Nobel Prizes that deserve them. And I've interviewed one recently, Giorgio Parisi, who actually came up with some theories of renormalization, and say he did win the Nobel Prize for complex systems in 2021. But he lost a Nobel Prize earlier. He could have had 2 Nobel Prizes if he actually claims he lost it himself. Jocelyn Bell Burnell discovered pulsars. Did she not lose a Nobel Prize? I've interviewed her. So it's kind of ridiculous. People have said, oh, you can't lose a Nobel Prize. But clearly, the interest that we had was it was worthy of the greatest kind of attention in science. And in fact, it received that up until the time when we effectively retracted the claim. And we did so by working eventually with the Planck team over the course of that summer and fall to develop a more accurate model for the galaxy's dust polarization, and found that it too could exactly make the amount of curl or B-mode polarization that we had ascribed to inflation with a given amount of energy and what's called primordial tensor perturbation power spectrum. So when that was said and done, we then effectively published a collaborative paper with the Planck team, and that showed great integrity by the leaders of the BICEP experiment and the leaders of the Planck experiment to get to the truth. And so it was disconfirmed. We did not measure the imprimatur of inflation. We measured exquisitely, accurately, the spectrum of dust in our galaxy. So it wasn't a blunder. We didn't leave the lens cap on. I always say we didn't put our thumb in the frame, as I'll do. We didn't intentionally obfuscate. We drew a conclusion that was premature. And it may be that there were gravitational waves embedded in the data, but they're certainly subdominant to the result we announced back then. Since then, BICEP has gotten better and better. In fact, it's better than any instrument in the world, even Planck, by almost an order of magnitude. So there's been probably $100 million or more spent to measure this signal, and there's going to be hundreds of millions more spent to measure the B-mode signal. And it's really gratifying for me to feel like I played a role in this whole economy of studying B-mode polarization experimentally back when I got fired from Stanford. So I think that the role of what we're trying to do now is still complete, and the BICEP team is to be commended. I'm not a part of the BICEP team anymore. I work exclusively on Simon's observatory, and what's called the Simon's Array, the polar bear instrument. And we are planning to repeat these measurements with much higher signal to noise in the Atacama Desert starting next month. We've built already 3 camera receivers, one at San Diego, one at Princeton, and one at Berkeley, and they're being deployed. The San Diego one is there now. The Princeton one arrived at the port this week, led by Lyman Page. The Berkeley one led by Andrew Lang, I wish, led by Adrian Lee, same initials.
Yeah, another collaborator of yours, right?
My good friend and collaborator, and really the chief architect of so much work that we do. Those are being deployed in the field, and we're going to have first microwave light this year.
Well, just a few things really quickly. One, the reason that I mentioned Daniel Wegner, the psychologist, is that he studied confirmation bias in the experience of free will and then various spooky phenomena like Ouija boards.
That's
and
right.
Then
Very
you
good.
also brought up politics in science. And this is something that I really hoped to talk a lot about in this conversation. You have a lot of criticisms about the Nobel Prize, and I learned a lot about the Nobel Prize and how it functions in science, but I think that's going to have to wait for another conversation because I really want to talk about the podcast a little bit before we finish. But the last thing, just to put a bookend on this segment of our discussion is that you mentioned earlier that the only way to overcome systematic errors is to build or construct another experiment just to isolate that noise. And how is your work with the Simons array oriented around this problem in part?
So what we do with the Simons Array and the Simons Observatory is kind of compensate for the lacunae or the gaps in the abilities of BICEP 2. And I should say the BICEP team has also recognized this lacunae and the what was not a fatal flaw, but it was a hampering of the scientific reach of BICEP 2, which is its focus on a single frequency. We wisely, at the time, built detectors that were only sensitive to CMB photons. That means we couldn't really see the dust exclusively or the CMB exclusively, but some complex melange, as they said. So what BICEP array in the future versions of BICEP, called BICEP 3, and the current fourth generation called BICEP array, and the Simons Observatory and Simons Array are doing is measuring at multiple frequencies, not
Hmm.
only at the 150
Yep.
gigahertz, 2 millimeter wavelength with the CMB polarization is the brightest, but also at higher frequencies and lower frequencies. And that allows us to constrain for each frequency band, we are constraining a possible foreground contaminant of systematic error. So we are in an extremely fortunate scenario. It's almost miraculous that we are limited by the galaxy. It's not like we're limited by the instrument or the detectors, and we're measuring signals that are millionths of a Kelvin. If you think about it, it's quite spectacular. When you look at imagine LIGO, which measured gravitational radiation directly for the first time in 2015. Imagine that signal was limited not by, as Barry Barish told me, hunters in Louisiana practicing target shooting on the interferometer tubes with their shotguns, or trucks rolling by, or seismic activity on the Earth's surface, or the tides on the oceans near Hanford, Washington. But instead, we're limited by a background of gravitational waves from inflation or from our galaxy or something like that. We're much more sensitive to astrophysical, but not cosmological signals than almost any instrument of its kind. So BICEP has done a heroic job. We are doing a heroic job on Simons Observatory to be limited not by instruments, not by statistical noise, but by astrophysical contamination. So
Mhm.
no matter what, we've got astronomy coming into the instrument, and we just have to suss out which component comes from the Big Bang, inflation, and which comes from the galaxy.
Hmm. Well, that's all. This is all great. It sounds great, and but now it's time to like totally shift gears for the last few minutes and talk about the Into the Impossible podcast. So, I, I mean, you've had some absolutely phenomenal guests. I know you just had Noam Chomsky on, which is amazing. But in particular, somebody I wanted to talk about is Eric Weinstein, with who I know is a good friend of yours. You've had him on many times, and the reason that I want to talk about this episode is it just came out a couple of days ago, and I just listened to it, and there was a lot going on that was quite interesting. And I mean, there are so many things that we could talk about in this short period of time, but one thing is geometric unity, which is his. I know it's still nascent, but it's his theory of everything. And I know you're not a theoretical physicist, but you're very close to the theory still. And how does GU resonate with you at this point?
Well, I look at all these potential theories of everything, and I think Eric would say it doesn't necessarily purport to be a theory of everything, but it's a unification of
Mm,
of
right.
quantum mechanics and gravity. Perhaps is the best way that he thinks about it. So there are multiple competing hypotheses, and there are snarky people out there. There are people that try to bait me into debating them, or having Eric debate them with conflicts. But what's my philosophy, and this is to all those people out there, my philosophy again is my job is not to prove Eric or Stephen Wolfram or Carlo Rovelli or Garrett Lisi or any of these people correct. My job is to prove people wrong. even if it's my good friend and very good friend, Eric Weinstein. So good, in fact, I've supported him and, for visits, and he's going to come back to UCSD to give lectures. I hosted his son for many months on and offline. And now he's an outstanding researcher, far surpassing anything I could have ever taught him. And so, but even with that, I am very open with Eric that my job is to, potentially prove him wrong. How do you do that? Well, you look at the concrete experimental predictions. And if you noticed on all my conversations, I've talked with all these gentlemen, Ravelli, Lisi, Wolfram, and many times with Eric, because Eric has a unique demeanor and a unique perspective, not only on physics, but also on philosophy, religion, life, politics, and sundry items. He's just a fascinating. I mean, it's no secret that he has so many people that just love him or hate him because he's so interesting. So
Mm-hmm.
we talk a lot. We also live close by, to one another, and we're very close. So when I talk with Eric, I ask following questions. What are the signatures in the CMB? I'm not a particle physicist. I'm not going to build a telescope on the moon, a radio telescope. I'm not going to build a particle collider that spans the solar system. So what experimental predictions could the Simons Array or the Simons Observatory or Polar Bear or BICEP, what could they observe that I could then obtain unique first look, first access data about? And to first approximation, it's completely agnostic as to what theory there is. We can do a Bayesian framework analysis where we ask how consistent are the data with the model. And that could be completely agnostic about how the model came to predict what it does. So Eric's model has predictions specifically of the nature of what are called spin 3/2 particles, which we don't have to get into what they are, but those have a very characteristic imprint on the dynamics of the early universe. And that can be shown theoretically, and then we can predict what would be the imprint on the CMB, on its polarization. And there might not be any. For example, Stephen Wolfram's theory of everything, the physics project that he works on, has a series of predictions about the speed of propagation of gravitational waves around black holes or emitted from binary coalescing black holes. I've looked at that. I've looked at what would be the CMB imprint. Would there be a manifestation in the primordial gravitational wave spectrum, not in the late time evolution of galactic and even extragalactic black hole coalescence? So I look at that. Lisi has this monster group E8 philosophy. To my mind, it doesn't predict anything that I can reach with a CMB experiment. So to say that, I'm trying to prove geometric unity, I think it's farcical. It speaks of a ignorance of what experimentalists do and the motivations for doing that. I can't speak to why somebody would be so obsessed with the fact that I am involved with testing multiple theories of everything or multiple cosmogenesis stories, right? So I'm not looking for inflation. I'm looking to prove inflation wrong. I'm looking to prove the bouncing model wrong. I'm looking to falsify the ekpyrotic model. I'm looking to falsify the conformal cyclic cosmology of Sir Roger Penrose. So all of that can be done. And those are all different, so which is more important? Discovering how the universe began, discovering how the forces of nature may be unified geometrically or in graph theory or in group theory. I think they're all wonderful. And I think you should let 1,000 flowers bloom. And to say, like, I'm not going to look at something, I think that he speaks in ignorance, as I say, of how experimentalists like me make our living.
Well, I've spoken with string theorists like Maldacena, or I've talked to Wolfram about his Rouliad, or Lee Smolin and loop quantum gravity. So I'll be very much looking forward to learn more about GU from Eric. But I mean, your conversations are very wide ranging. I mean, some of the other things that I had wanted to ask you about were your thoughts on his interest in the Galileo project and Avi Loeb's work, and how this might be important for getting us off this planet, or you also talk a lot with him about the state of universities and tenure. And this is all really interesting and gets into the politics of science. But for now, I mean, I've waited to have this conversation probably for about a year, and it was so worth the wait. It was so great to talk with you, Brian. Thanks so much for your time.